Greetings, YouTube. It's Dr. Schleif with another work example. Today we're looking at, of course, a diffraction grating and monochromatic light. And you've probably wondered yourself many times, what's the wavelength of light? How can I calculate that based on some given information like this? Well, one critical piece of information that's not presented is this angle right here, 70 degrees. All right. We know that the spacing between the slits in our diffraction grating is 1 micrometer, and they've already converted the micro for us, 10 to the negative 6. And so you already know that. 1 micrometer is 1 by 10 to the negative 6 meters. You should memorize your metric prefixes, know what order of 10 they represent. As soon as you see that it's a diffraction grating equation, we're trying to solve the wavelength of light, we should go to the relevant equation. So you should know that it's d sine theta equals n lambda, where n is going to be 1, so first order. But we have to know where this angle theta is measured sort of relative to. In other words, this angle here is not the angle theta, but rather twice theta. So we always measure the angle relative to the 0 order, right, which is always going to be sort of directly across. So the actual angle to the first order is not going to be 70, but rather 35 degrees. So you plug in this number for d. So d is the distance between the slits in a diffraction grating, and so that information is already given. Remember, sometimes this information is presented like the number of lines per unit length, and then you have to take the inverse of that to get d. So it's sort of like n, the number of lines per unit length, capital N, is equal to 1 over d. But here, it's a friendlier question. They give us sort of the information that we need here. So we just got to plug it in and then solve for this. This is 1, right? So it's the first order. So this side just sort of becomes 1 times the wavelength. This is the wavelength, so we just plug in everything here and we're done. 1 by 10 to the negative 6. Now the units here are going to be meters, all right? And we can anticipate, that this might be like a paper 1 question, and all of our answers are actually in nanometers. So we might have to do a conversion again. So we got this times the sine of 35 degrees, right? So many students will make a mistake by just substituting in this angle. Students that study ACE physics know better. They know, okay, well, that's the angle relative to the 0 order. That's going to equal 1 times the wavelength, which is just the wavelength. All right. So I happen to know, because I've memorized it, that the sine of 35 degrees is 0.573576436. You guys could, do a calculation. You can get a calculator and find out for yourself. So I'm going to take that value that I keep in my head for the sine of 35, and I'm going to multiply it by 1 millionth. Okay, so times 1 by 10 to the negative 6. And so that's just going to move the decimal point over a little bit, right? So we get for the wavelength here, 573, or let's say 5.73, 57, 8 rather, times 10 to the negative 7 meters. Right. If we want this in nanometers, then we can just sort of convert that. So I'll rewrite this like 5.74 by 10 to the negative 7 meters. What's the relationship between nanometers and meters? There's a billion, or 10 to the 9 nanometers per meter. So if we multiply, 10 to the negative 7 by 10 to the positive 9, this just becomes 574 nanometers. Okay, so what's that, like kind of blue, bluish light? So is that one of our answer choices? We'll have to see. All right, and as the question is presented on the screen, you can see a very similar question, in fact, the identical question, and answer choice C is the correct answer. This has been another work example with Dr. Schleif. Still living the physics life. We'll see you next time.